So we left off of this graph. And this graph, we said, was generated just like a traditional calibration curve. The only difference is the blank, right? The blank's not really a blank. There's actually signal associated with it. And we went into this knowing that. We said that the blank was really a sample. The sample's got a component I'm looking for. Because it's present, there's going to be a positive signal, and that 0 mark is actually going to start way up here. But we still get a linear regression line, and we can still get y equals mx plus b, and we can still get an r squared value. No big deal. It's all there. But the problem that we left you with in the last video was, how on earth do I know how much is present in that sample based off of this information? Well, here's what we do. One, you have to understand a little bit of math. Know that this linear regression line, ideally, can go infinity and beyond in both directions, not just one. Now, we know, we've already talked about it, non-linearity. We said that the instrumentation can only go up so high, and then the linearity of the curve begins to fail. Nothing that you've done as far as sample prep goes. It's just the limits of the equipment. That's it. But it goes both ways, people. If it can go this way for a little bit, it can actually go this way for a little bit. And we can extrapolate the data. I just pretend that that line goes backward. And I've done it as a dotted line. And the reason that I've done that is because this axis also goes backward, right? Just like it goes forward. And here's the magic of the graph. If I can figure out where this extrapolated line crosses the x-axis, right there at that spot, this is the concentration of the component that's in the sample. It's as easy as that. I just have to understand how to get Excel to do that for me. That's it. That's all that I've got to do. So I need to extrapolate the line backward. I need to figure out where that crosses the x-axis. And if I can do that successfully, then I will get the concentration that's represented on the x-axis, right? Okay, well, if I take a look at this, it kind of looks like that is where y is equal to 0, right? So the x-axis goes left and right. That's my x-axis here. I get negative numbers and I get positive numbers. Negative to the left, positive to the right. Well, the y-axis goes up and down. So at y equals 0, which is right here, that is where the line is going to cross the x-axis. It's the x value that I want to solve for. So if I've got my y equals mx plus b equation, the only thing that I'm going to have to do is put 0 in for y. And then I solve for x. And that x number will be negative, because this extrapolation happens on the left-hand side of the origin. So when I solve for this equation, you are going to get a negative number. And this is okay. We know that going into it too. We just pretend like the negative doesn't even show up. And whatever number is present, all of a sudden, that is the concentration of that component in the sample. So the graphical representation is going to be much easier to work with. And we'll do an example of that using Excel so you can see that in just a second. But this is how we get graphical representation with the y equals mx plus b, plug 0 in for y every time, and solve for x. And that will tell you the concentration of the sample that you analyzed. All right, so now I'm going to flip it over to Excel, and we're going to crunch some numbers, and we're going to see how this process is going to work. So here is my Excel spreadsheet. And what I've done is that I have just pretended like we had made a set of standards. And let's say that we are looking for benzene in the gasoline. Let's not change our example up. And this was the concentration of benzene that I have added into the sample that was presented to me. So this is my blank. It's just the sample. I didn't do anything to it. And we're just going to run it. And I get a signal. And that's because benzene is present in the sample. So of course I should get a signal. Well, I've made a set of standards after that. And I've added more and more and more benzene to the sample. And then I reran it. So this one I've added 2 part per million. And then 4 part per million I added. 6 and 8 and 10 part per million. Again, I know how much is there. I know how much I've used. I know how much volume that I've ended up with in the end. So these are my concentration values. And then I run each one of those standards that I have made. And I get these absorbance values. Or signal. So how do I solve this graphically? We're going to start with that first. Well, you do this just like any other calibration curve. Here's your standards. There's your absorbances that go along with them. I'm going to highlight the data. I'm going to go to Insert. I'm going to go to Scatter Plot. And then I'm going to choose the one that has all the dots just like before, like we always have. And there we go. And it looks like a calibration curve should look like. It's linear, and that's what I should see. The only difference is that it doesn't go through the 0.00 down here at the bottom. And again, that's because my sample has stuff in it. And my sample is regarded as the blank. I didn't add anything to it. It was already there. So, of course, it's going to start up a little bit higher. Well, you do what you've always done. You click on the data. You right-click. You go to Add the Trend Line. You come down here to the bottom, and you hit Display the R-squared, Display the equation. None of that has changed. All of that is the same. Just as with the calibration curve should. So I'm going to click on the data again if this screen disappears from you. And it should pop back up. That's where you found display the equation and display the R-squared value. And there's a thing called forecast. And there's a forecast forward and a forecast backward. Remember what I said? We need to extrapolate the data backward. And if we can continue that line to the left-hand side, then we maybe could get a better idea of where this thing is going to cross the x-axis. Now, I don't need to see this graphically. I can just use this equation, plug 0 in for y, solve for x, and that will give me the concentration. But sometimes we like to expand the graph, and we like to see exactly where that is to make sure my math is okay. So I'm going to play around with the forecast. Well, in the backward, notice the unit is called period. Well, I can just play around with the numbers. If you can eyeball it and estimate it, it looks like it would cross maybe over here somewhere. That's the equivalent to maybe between 2 to 4. Who knows? But you can play around. So put a 1 in there and see what happens. So I'm going to forecast backward. I put a 1 in, and notice how it continued the line to the left. It's not really crossed the x-axis yet, but it's getting closer. So I'm going to put a 2 in. Now it's extended that line even more. Notice it still hasn't crossed the 0 mark. It's still there. So I'm going to go up and I'm going to put a 3. That's extended the line even more. It still hasn't crossed yet. So let's put a 5 in. And now I have crossed the x-axis, right? So here is the 0, 0 mark. That's the origin. And if I come over to the left, I'm going to keep ticking on until I see this graph cross. And right there is where it crosses. And it looks like it's in between -2 to -4. It's going to be -3 something is what this thing looks like. And that is going to be the concentration of the component that was in the sample when I brought it into the lab. That's how we do it. We do a backward forecast. Now, graphically, that's how you represent it. But again, I don't really need that information to solve for this graph or to solve for this sample? We said we just need the equation, right? But graphically, this helps me maybe see it a little bit better. I kind of know what to expect now going into it. So I'm going to switch this back over, and we're going to write in the equation. So y equals 0.0647x. So y equals 0.0647x. And then I'm going to flip back, and it looks like it's plus 0.2052. There's my equation. It's what I need. Well, I told you if we can solve for x, x is the concentration, right? And that's where y is equal to 0. So 0.0647x plus 0.2052. To solve for x, you're going to subtract 2052 from each side. Well, 0 minus 0.2052 is negative 0.2052. And then to solve for x, we're going to divide by 0.0647. And x is equal to, well, let me pull up a calculator. 0.2052. I'm going to change that to negative, divided by 0.0647. I hit enter, and that gives me negative 3.17. Now, we said the negative doesn't really mean anything. We knew it was going to be negative, right? If I go back to that graph, we knew that we were working on the left-hand side of this, and that's okay. We just pretend in standard addition that that negative does not show up. So 3.17 is going to be the concentration that's in that sample. Now, what does that really mean? Well, that means that in my sample that I didn't add anything to, it gave me a signal of 0.214. That signal came from a concentration that was around a 3 part per million. So what I've done is that I've taken that 3 part per million, that was my blank, I added a little bit to it, I've added 2 part per million, so that represents really a 5 now, right? I've added 4 part per million, well 4 plus 3, that's really a 7. I've added a 6 part per million, 6 plus 3, that's really a 9. So I've added more and more and more component, which made my absorbance go higher and higher and higher. So if the question is, how much is in the sample? Well, you just solved for it. 3.17 part per million. That is what gave me this signal that I got from the blank, which is really the sample that was provided to the lab. All right, so that is how we graphically solve for standard addition. And what I would like to do in the next video, I would just like to go over another example problem. I would like to give you real stuff, real standard prep. That way we can work through all the math and kind of figure all of this out together, graph it, use Excel, and then solve for this equation all over again, just so you can see a full-blown example problem from top to bottom.